I want to talk about how to make sense out of signals, and adding with artificial intelligence, can we actually develop a model that can make sense? What is the sense here? Human activity detection, in other words, what are the human beings doing in the room? And using artificial intelligence to predict or guess or identify, it's actually been going on for some time. Before I get into the topic, my name is SK. I have a long name. I work for Digitalist. We are into deep learning, and that's it in terms of marketing. Okay, before we get into any further, if you have seen this picture, please don't answer the question. But if you're not, tell me, each picture has a number. You can't see it. 1, 2, 3, 4, 5, 6. Which of these, one or more than one, is a fake picture? In other words, not a real human being. Who's that? Okay, anyone? More than 6? Or 1 and 6? Okay.
And
2.
2. And 5.
And 5, okay. So maybe I should ask you which one is not a fake, which was a real human being. Come on, you're not going to be penalized. Sorry?
They all look kind of fake.
They all look fake? Okay. So you said all fake, you said all fake, you said a couple of guys are fake. Did you say all fake?
I said.
Oh, you said, okay, sorry, yeah. Sorry?
You're asking if they're real people, right?
Mm-hmm.
They're obviously two-dimensional representations of a person.
The pictures of real people.
Okay.
Yeah.
So not Photoshopped?
Not Photoshop, yeah. All of these pictures are fake. These human beings don't exist. These are made by machines, AI machines. It was actually amazing, and NVIDIA posted it, and there's a link right there. You can go and check the NVIDIA site. After, I think, 16 hours or whatever, I think, of training, AI machines could figure out. The last 2 years, especially 2016 and 17, has been a golden era for image processing in artificial intelligence. Whether it's still images or videos, lots and lots of companies have actually developed solutions that will actually process the videos and figure out what's happening. For example, I read a paper a couple of months ago, published I think around 6 months ago, by an Israeli university, which will bring a static image to life. I know you might have already seen in your iPhones and regular phones, but the way this model brings the static image to life is, if you post it, let's say, on your Facebook profile, and if your friend looks at the picture smiles. If your wife or boyfriend or girlfriend actually looks at it, maybe I think it does something naughty or funny. If your kids or siblings look at the picture, it actually does something which is more appropriate, whatever is appropriate there. And this is not just a couple of wrinkles on the face. This is a complete transformation of a still image, which make you believe that this picture has been taken the way it's doing now. That's one example. Of course, there are a lot of other examples in image processing. But there are problems in image processing using AI models. Privacy is a big concern. People don't want their pictures to be taken, number one. Number two, line of sight is an issue. If you want, let's say, your image processing model on a surveillance camera or a drone, the camera has to actually have the sight of the thing or a picture you want to take. Otherwise, the model does not know what you're doing. Number three, what if it's dark? I know of a company in Berkeley which is processing images of Alzheimer's patients to find out when a patient actually is slowly sitting on the bed or slowly falling onto the bed. The difference between sitting on a bed and falling onto a bed by an Alzheimer's patient, apparently, only a trained medical doctor or a nurse can only figure out. But they're working on a model which actually can develop a model which actually can figure out when the patient actually is in control or not in control. And then you can bring in a nurse to take care of the patient if this needs attention. All of these situations, which have been actually worked for the last year and a half and 2 years, are becoming problematic because of privacy and so many other concerns. Wi-Fi signals being used to track human activity has been going on for some time, especially custom-made sensors or radars being used. Even as simple as if you have a Fitbit or an Apple Watch, which actually tracks your number of steps and all of the stuff, this is being done for some time. But using Wi-Fi signals, commercially off-the-shelf router Wi-Fi signals, and predicting human activity is something which has been happening very, very recently. This research I'm going to talk about today, I'm actually going to share a few papers about what has been published. This is so recent. Some of the earliest papers where people used different types of signals was done with very rudimentary applications without AI and with AI. But when I say earliest, that's as early as just 2014 or 2015. 2016 and 17 is when people have started doing a little more stronger research using Wi-Fi signals. And 2017, I think around the last 6 months ago, people started using deep networks to process Wi-Fi signals. What are some of the use cases people have been using Wi-Fi signals for? There are papers available which will talk about models being developed using Wi-Fi signals to track the size of your indoor stadium, the temperature or lighting control, or even as unique as if someone is speaking, Wi-Fi signals can understand what you're speaking without even doing an audio recording of it. So the lip movement, there is a fantastic paper published which does lip reading, but that's more of image processing solution. If you guys want to read that, I think you should look for lip reading in image processing using AI. They even have a YouTube video which actually does the demo, where if you mute a television news reader, the model will figure out what the person is talking and actually types the text or does the audio for that. But that's image processing. In this case, they've used Wi-Fi signals to actually predict what the person is speaking. Of course, majority of the research in Wi-Fi signal processing has been happening in the healthcare sector, trying to find out when the patient is walking, sitting, lying down, or even to the extent of breathing, which when I read the paper was very, very amazing. I'll talk about some of those papers and take you through the history of what happened in Wi-Fi signal. The research I'm going to talk about today, it is still happening. I don't think it has been adopted by the industry, especially Wi-Fi signals in the context of deep learning models. I don't think it's happening. Again, it's my limited awareness. In the academic circles, papers are being published of using Wi-Fi signals. Initially, 3-4 years ago, they were using RSS signals, received signal strength. But off late, for the last year and a half and 2 years, people have been using different types of signals within Wi-Fi routers. Also, the trend is going towards how can we use commercially available Wi-Fi routers without making any hardware changes so that you already have them in houses or indoors or offices or stadiums. And also, the recent trend is to use deep learning models. Of course, a couple of papers I will show which has used the regular machine learning models where some sort of a machine learning classification models were used, but they're not very, very effective. And I'll talk about what are some of the problems still not answered in the Wi-Fi signal processing industry, which is what is stopping or slowing down the AI research. But I guess in the next couple of years, you will see tremendous number of papers published. The reason I'm giving you this context is the research I'm going to show today is not complete, it's not comprehensive yet enough. I don't have the awareness myself in terms of what is the right solution for some of the problems I'm going to talk about. But this topic of using Wi-Fi signals to predict human activity has been so recent, but at the same time has such a great potential. I personally believe in the next 2 years you'll find lots more research and a lot more adoption by the industry to actually take it further and show results. A couple of years ago, when the Wi-Fi signal processing was being introduced, lots of companies, academic institutions have used RSS signals, received signal strength, which is more of a reflection of the power of the signal, the signal strength. And on top, people have used a few classification models. But the problem in that process is the signal strength is never consistent. It actually gets affected by so many other external factors, including, of course, the temperature, humidity, and air pressure, and all other stuff too. But more importantly, the signal which the router is emitting is never consistently strong enough. So people actually move to something else called channel state information. When you have a signal that comes from a router, so you have a transmitter and receiver, if you use a MIMO, that is multiple input, multiple output system, if you have multiple antennas on a receiver, each receiver receives the same packet, and if it's an OFDM system, you actually have 30 subcarriers. In other words, every antenna is transmitting the same packet using actually 56 subcarriers, but you actually have access to 30 subcarriers. So the same packet is being transmitted by antenna 1 of the transmitter and received by antenna 1 or 2 or 3 of the receiver. The same packet is received. And the way you model the receiver packet versus the transmitter packet, I'll show you a mathematical equation on how to figure out the channel state information of a transmitted packet. The reason there's more research happening in using CSI is the CSI data comes closer from the physical layer of your router, and hence the signal is consistent, relatively consistent. At the same time, the impact of external factors, even though there is impact, especially on the amplitude because of the obstruction of these signals by objects in the room or human beings or moving human beings, the information of the CSI information is relatively stable and standard for people to get the data, process the data, and see if we can make sense out of it. Yeah.
You said something about OFDM?
OFDM.
What does that mean?
Orthogonal frequency division multiplex.
There you go. OFDM. Yeah, that's it. That's the system that's being used in the modern Wi-Fi routers to let the packet being sent from multiple antennas and multiple subcarriers so that the transmitter will receive at least a few or all of the packets so that you don't miss any of the packets. Yeah. In CSI actually is composed of amplitude and phase. So when you have a packet that starts from a transmitter to a receiver, it actually has an amplitude. So it actually has a wave, it's an amplitude, and also has a phase information. Amplitude does get impacted a little bit because of obstruction or multipath, or sometimes even fading, because it over a period of time, based on the distance, it actually starts fading too, but that gets a little bit of impacted, not as much. Phase is, even though it's not that much impacted, what normally happens is because of the manufacturing defect or manufacturing situation, there is lots of noise that comes in along with the wave. So when you capture the CSI information about a packet at that receiver antenna, it actually has lots of noise too. If let's say the received packet is denoted by YI and the sent or the transmitted packet is XI, by the time it receives at the antenna, the receiver, it goes through a transformation which is impacted by something called HI, which is nothing else but the channel state information in this case, plus some noise. This is the most fundamental equation I want you guys to take away today. Yi is equal to Hi times Xi plus Ni. Ni is the noise. If you can reduce the noise, then Yi is directly related to Xi. That is, the received packet is directly related to the sent packet, but influenced by the channel state information. And capturing channel state information has become almost very easy now, because some of the NICs, the network cards available in some of the laptops, can easily capture the information. I am more of a deep learning guy. I'm more of a AI person, less of a signal processing person. My effort is to see how I can capture the data. Once I got the data, I would rather jump in and start doing the AI models. I will explain some of the papers people have published in processing this. Any deeper signal processing questions, I think I can get back to you later on, but we can talk about the use of this data to develop deep models. Towards the last, I think I'll talk about a real deep model, which one paper is published, but I'll also talk about my own research, not published. You can take it. I know it's being video recorded, but I'll try to be vague enough so that you can't use the information as is. But there are a couple of ideas which I'm working on, which actually using deep models, both LSTM and CNNs, and using CSI data and make more sense out of it. You had a question?
Is HI the nth column in the H matrix?
The H1 to H30, these are the number of subcarriers? What was the question actually? Maybe I missed a question. HI is a matrix, yeah.
Is HI the ith column?
HI is the matrix, but the I is more of, which denotes the number of carriers that's coming in. So if you let's say if you have a number of antennas, your H matrix will be, for each antenna you actually have so many subcarriers information. So this H1 would be the CSI information of that specific packet coming from antenna A to antenna B. So for every packet, you actually have a matrix of number of antennas times 30 matrix that comes in for each packet. So let's say if you have around 1,000 packets, the same packet that goes from transmitter to receiver, then you have so much of data that's come in for each packet. And if the location of your transmitter and your location of your receiver don't change, the information what you're getting is consistent enough. And then you can use that data to make extrapolation and feed it into your deep learning models to actually start making sense.
So I didn't understand that equation nor the matrix. So is S 30 to 30 in that thing?
S is the number of, I think, number of antennas. Number of antennas you have. If it's a MIMO, if you have a 3 by 3 antenna, you have 3 transmitter and 3 receiver.
Okay.
And the number 30 is the number of subcarriers. For each transmitter receiver pair, let's say if you have 3 transmitter antennas and 3 receiver antennas, you actually have that is the first antenna of your transmitter will send packets and received by all the 3 antennas of the receiver. So if it's a 3 by 3, sorry?
So there are 9 pairs.
It's a 9 pairs, yeah. And if for each of the packet that goes in has 30 subcarriers. So you actually get information of the same packet from 30 different subcarriers. So the small hi would be the CSI of that packet for that transmitter pair. And if you want to have the entire CSI for a single packet for the MIMO of 3 by 3, then you'll get a matrix like this. And that's for one packet. Let's say if you want to collect lots of packets, then you have a sort of a tensor, more than 2-dimensional, 3-dimensional matrix information for that set of packet. So let's say if you have a lab setting where you have a transmitter and receiver, and if you want to track that walking of a human being, and you want to develop a model that predicts whether a person is walking or not walking, just to make it simple, two binary situations, walking or not walking, then you can let the person walk for X number of minutes and not walk for Y number of minutes, and capture the number of packets you have transmitted during that duration and find the CSI value for each packet. So you have CSI packet that's coming in consistently over a period of time. If you break that time into, let's say, a few milliseconds, let's say 20 milliseconds or 50 milliseconds or 100 milliseconds time period, you actually get so much of CSI data, so much of matrix. And now you have data and you have the labels too. That is, you actually have some CSI which is labeled as walking, some CSI as not walking. Then the whole thing gets transformed into a deep learning solution, an AI solution, no more just a signal processing problem. So the first couple of slides I want to really talk about what type of data was collected by Wi-Fi signal engineers using AI models. As I mentioned to you earlier, RSS signals were being captured, but off late it's more of CSI signals. CSI signals are a lot more standard. I'll show you another slide where the phase and the amplitude information is a lot more consistent compared to RSS signals. So right now that's what is happening. Towards the last slide, I think I'll talk about what is coming in the future, what seems to be stopping or rather slowing down the research of signals using AI model is the type of data itself, and I'll talk about it in the last slide.
Question: you have the transmit and receive antennas. Are you assuming equal number of transmit and receive in this model, or?
In this model, yes. Yeah. So the MIMO in this case, I think 3x3 seems to be the most common commercially available, but I think there may be unequal number. It's possible, but I think in this case, what I have seen is all the papers I have seen here are using same number of transmitter and receiver antennas.
Transmit meaning at the access point or at the device?
At the access point.
So transmit and receive at the access point.
Mm-hmm.
You're receiving on this device.
On your device, let's say your laptop or a cell phone.
You might have 3 antennas, right?
Well, if you use a laptop NIC cards, they actually have 3 antennas. That's what I think I know.
You're assuming a symmetrical system.
Yes, yeah, at this time, yeah. I've seen a couple of papers where I think the number of transmitter antennas and the receiver antennas are dissimilar, but I think the few papers I've read is all talking about similar antennas on both the situations. So from now I'll talk about, once we have the data, how to start processing it, how to use maybe machine learning models and deep learning models, but I want to emphasize the point that the data collection is one of the most difficult problem in this case. I'll give a couple of examples. The objects in the room, even if it's a lab setting, and if you want to only detect human walking and there's nothing else obstructing the path, you also have the walls and the roofs on the floor. The reflected signal is getting impacted because of the reflection. Also, I think fading is happening. So even though the CSI signals are a lot more stable compared to RSS, CSI still gets affected a lot, number one. Number two, noise is a huge factor. I will show you a couple of examples about how you can do denoising of your signals, and that is still a huge factor, and people are trying to figure out how to do that. Number three, the time duration of your data snap. Let's say if a person is walking, and of course the person can walk for 5 minutes and 10 minutes or 15 minutes, but let's say if you want to detect a human being sitting, and typically sitting takes maybe 1.5 to 2 seconds. Now, way to draw the line in sense when does the sitting start and when does the sitting end is a data collection problem. Sometimes if you don't have the clocks of both the transmitter and the receiver is synchronized, then you have a problem, there's a delay. And even otherwise too, if you have accurately labeled the signal about the start and end of an activity, because an activity takes some time, 1.5 to 2 seconds, if you define a model that, okay, my data point is, this is a CSI for sitting, it's difficult to find out what CSI signal you're taking, because CSI, that happens over a period of 1.5 seconds, and you actually have multiple CSI signals coming in that time period. So that is another complication, and maybe it's a good thing too. I'll talk about the deep learning models which actually can take care of the temporal effects, because if an activity can take not just in one timestamp, that is t is equal to not just t0, but t is equal to t0 and t1 and t2 and t3 and t4, then how do I take all these 4 timestamps as an input and make sense out of it? Can be done only in deep learning, but not in regular machine learning. Anyway, so once you collect the data, the standard algorithm or standard approach being taken is you collect the data, you do a little bit of a denoising, and then do a feature extraction. Feature extraction takes place only if you're using machine learning. Let's say if you're doing some sort of a classification model, like a k-nearest neighbors or SVM or any other models, you do feature extraction, and then you do the machine learning model on that. The advantage of using a deep learning model is you don't actually have to do any feature extraction. Model will figure it on its own. And that's why I think the last 2 papers I'm going to talk about actually talks about the deep learning models where there's no feature extraction. A couple of papers very clearly talked about denoising. Again, if you do the research on signal processing, I think there are lots of techniques being mentioned about how to do denoising. There's lots of filters you can pass the signal through. You can get some noise out. Butterworth loss, the low pass filter apparently is a lot more popular, but it's not as effective, especially for the CSI signals. There are a couple of other filters being used, but the most popular denoising technique for signal processing is using PCA. PCA has been used in regular machine learning models too, but it's most effective in signal processing. You have the principal component analysis, where you can identify the individual signals which form a part of the combined signal. You can actually delineate the individual components of the signal, and whichever signal is contributing or the noisy signal could be eliminated. I'll show an example of a I'll come to it. So PCA, I think if you are developing a signal processing model for deep learning or machine learning models, I think PCA would be one of the first things you would do. This is an example of just the amplitude and phase being sanitized. If you look into the signal here, this is just the reflecting the amplitude part, and this is the phase information. The accurate phase or phase change or phase difference is not effectively captured if you're not sanitized it. Some sort of sanitizing has to happen. The carrier frequency offset and sampling frequency offset are 2 very technical signal processing terms. I don't have too much of a detailed information, but carrier's frequency offset is a reflection of sometimes the way the product has been manufactured, and hence CFO and SFO are inherent noises available in your signal, and you got to figure out how to process it. And if you process it and do a sanitization, you actually can see signals very clearly changing the phase or the amplitude to reflect the activity of what you're trying to predict. So the more distinct the data is, the better the model can figure out. And that's what we're trying to arrive at in this case. If I have to compare this with an image processing model, which we have worked on earlier, you actually have an image where a person is standing or walking. The pixels in an image are changing. You actually have a very distinct pixel numbers available that you can tell the model, okay, this is what the pixel intensity is when the person is walking or sitting, and the model can immediately figure out. But in this case, there's so much of noise, and hence you got to take the noise out first.
Question, is the outcome here to figure out with PSI the range or the location?
The location of...
But when you zoom in activity detection,
okay.
Are you trying to figure out how far am I from the access point?
Okay.
Or are you trying to figure out where am I located relative to the access point?
In the next few slides, I'll be talking about multiple efforts done in localization. In other words, to predict where the person is, where the person is located. There are a couple of other papers which talks about what the person is doing. So human activity detection is a couple of other research too, but localization has been one of the earliest research being done. I think in 2012 there are a couple of papers I'll talk about. I'll come to that paper. I think I don't want to. But before I get into the deep learning models for signal processing, I want to explain two fundamental building blocks of deep learning. If you guys have heard of LSTM, I think it'll be nice. If not, I can explain. There is a model called recurrent neural networks. A recurrent neural network is a deep model which takes data in a temporal fashion. That is, if something has happened in a sequence, and if there is an importance assigned to the sequence, then this would be a fantastic model which actually can take the information one after the other. RNN, there are variations of RNNs available. One variation is called LSTM, long short-term memory. This has been hugely popular for the last 3 or 4 years in LSTM. If you go to some of my YouTube videos and blogs, I talk about LSTMs being used in text processing, for summarization, question answering, and all of that stuff. There is one fundamental problem in RNN which is addressed in LSTM, and that's called vanishing gradients or exploding gradients. In other words, if the temporal information you are inputting is very long, then RNN starts forgetting the information that it heard first and only remembers what you fed in the recent past. Let me give an example. If you want to, I'll give a non-signal processing example and a text processing. If you are developing a model which will do summarization of long text, and if you want to feed the entire paragraph into the RNN, after the 20th or the 30th word, RNN starts forgetting what was the first word, what is the second word, and then you have a model which is forgetting things and it's not very effective for you. So you want the model to remember as much information as possible because you want to feed all the information for the model to make sense. So from RNN came LSTM, where the model actually has some memory in it. And according to research, RNN can remember a maximum of 10 words or 10 input data points in a temporal fashion. And the reason I'm talking about RNNs in signal processing is, if your timestamp of the signal, especially for human activity detection, if the person is sitting down and the person takes, let's say, 1.5 seconds to sit down, and if your timestamp is, let's say, 100 milliseconds, you actually have 15 data points for that single activity of a person sitting. And for all of those 15 data points will be different from each other. And hence you want to feed all those 15 data points and tell the model, okay, this is altogether an activity called sitting, because there's no one single instance activity. So from that sense, LSTMs need to be used. If you are into signal processing research, especially in deep learning model, take it from me, there's no single paper published yet on signal processing or human activity detection using LSTMs. We are working in our company on using LSTMs, but if you guys want to work on that, that'll be nice. How? I won't tell you. Second is another deep learning concept or a model called CNN. CNN actually takes images, and if you look into image of, let's say, the smallest size of 224 by 224 pixels, each pixel has a number given, and using CNN, you can run a filter on the image, do a lot of processing. I'm not explaining the whole convolutions and subsampling activities in a CNN model, but CNN is another deep learning model which has been used in one paper, I think not prevalently used, but I think it's going to be used more to, if you convert the signal data into some sort of an image, you can feed that image into CNN models for the model to make sense. So even though the accuracy of human activity detection as of today, published by papers in 2015 and 16 and 17, is as high as 90, 94, 96%, many times the accuracies are in a very, very restricted lab environment. They have not been used in public environment, in a non-restricted environment. And I think the limitation of the non-deep learning models, non-deep learning signal processing models, is because of that the signal is not very consistent. So this is one of the earliest, couple of earliest papers in 2012. In both the situations, they used RSS signals, and the receiver signal strength was used to make prediction on the distance of this localization. In this case, is the distance of the person, how far away the person is located from the receiver. That was the prediction done. So they developed some sort of a database of, if this is the signal strength with accuracy 60-70%, plus or minus so many X number of meters is the distance the person is located. One of the earliest ones, even though the accuracy was very high, but they were using RSS, not very effective.
So what was the accuracy and how far was the range?
I don't recollect the exact accuracy in this. No, I can't recollect. So the accuracy was, I think, very high, but they were actually developing a database based on the signal strength received. But in both the situation, if you see that they used RSS signals, but nowadays people don't use RSS signals because they're not very consistent. That's the reason why I didn't.
A room, or was it a big hall?
All of these papers were in a lab setting of, the smallest was 3 meters by 6 meters. The biggest was, I think, 14 meters by 11 meters lab. So it's the smaller than this room, definitely, for sure. All the experiments till now. Yeah, I don't think there were a couple of papers I did not share in the presentation today, but there are a couple of presentations which talked about detecting, making a machine learning model to detect the lighting arrangement in an indoor stadium. But of course, the stadium is massive. But there they were approximating lots of signals coming back as a reflector signal. I did not mention that in today's presentation, but because the application of that research was not useful in other contexts. Whereas in a small lab environment, I found the repeatability of the activity was higher, and also the accuracy was higher. 2014, this is the first time I think I've seen them using some sort of a machine learning model, SVM, support vector machines classifier. But except that being the difference, all other activities are very similar. They collected the data, they did some denoising, that is increasing the quality of the data, try to identify anomalies, that is local outlier factor, because some signals were completely out of the norm when they looked at the average numbers of signals coming in, so they had to remove the outliers, and then they did just a support vector machines. Support vector machines, actually, it will give you a decent accuracy of whether the person is located in X number of meters away or Y number of away meters. If you are having two classes, if you have multiple classes, then you can do that too. But then you are restricted on the number of classes you have defined using SVM. And that's one of the earliest papers. They actually had good accuracy using this model, but they actually were focusing only on the fall detection of a human being. When the person walks, of course, the signal varies in a certain way, but the person sitting down versus falling down, even though the signal looks very similar, but on a frequency domain signal, you see too much of violent up and down going on in the signal when the person is falling down. They banked on that information of the signal, but in other words, in this model, there's not much of difference from what I mentioned earlier, except they've used SVM classifier. 2015, there's another one which is more of they created a bunch of fingerprinting of human activities. So here they used both RSS signals and CSI signals, but they found CSI was a lot more effective. They were focusing on two different activities: washing dishes and talking on the phone. Whether the person is washing the dishes or talking on the phone. And for them, they were using more of, I think they used what, HMM? Yeah, they created histograms. All the signals were converted into histograms and identify what type of histograms fall into either of the bins. If the two bins, washing dishes and talking on the phone, are two different bins, how effectively can I delineate the signals coming in and put into multiple bins? And this is the model they have used. But this is more of a this paper I wanted to highlight not for the deep learning or the machine learning model approach, but I think they did a lot of cleaning up of the data. If you want to find out more techniques on how to clean up the data, especially signal or denoise it, this would be a good paper for you to read. This is one of the earliest paper which in 2015, a good approach if you guys want to use it to they tracked 4 different activities, I think, sitting, standing, walking, and falling down, I guess, 4 different activities. And if you look into just the wave, the different types of waves for walking and falling and sitting. If you look into the falling and sitting down, look at this portion of how the wave is responding. Whereas this portion of the wave seems to be similar. In other words, the CSI numbers for walking, for falling and sitting down is similar, except towards the later part, because the person, when it starts falling, the signal responds almost similar in both the situations, still half the fall, kinda, and when the real fall comes, I think the signal starts responding differently. So
dB, or what's
the amplitude is in dB, yeah.
dB?
Yeah.
So it's relative dB between, is it relative or is it an absolute measure? You look at the difference between, because 20 dB is a big number, right? That's a big number.
Yeah, I wouldn't know. I don't know whether it's relative dB or not, but I know it's a dB where they're collecting the amplitude changes of the signal over a period of time for the entire activity that's happening. I think it takes almost 2 seconds for the person to fall, and for that, in that 2 seconds period, I think they've taken the amplitude. Whether it's relative or not, or absolute.
It's really high because 3 dB means half the signal loss. 20 dB means it's like, 100,000, whatever. Right? So it's very steep decline in amplitude.
Maybe I'm not an expert in signal processing, so I would not know. But whether it's relative or absolute, but I know it's dB.
So this is showing that how would you know when it's a fall? How would you detect that? When you're training the model, you actually have a human being falling, and then you actually collect the CSI data. So once you collect the CSI data, you actually start using a classifier model to identify, okay, which of this new signal that's coming in is similar to walking or falling or sitting. So you do the comparison. So when in a typical machine learning model, you train the model, and then when the training is done, you actually infer the model. And this is when you're training the model, you get the information and then convert it to CSI and do classification later. 2016, I think this is another famous paper where a person was walking up and down and then trying to capture the amplitude. This is an example of a PCA. If you look into the same signal as you do PCA analysis for 4 different components, you can see this particular signal is too violently shaking, which is creating more noise. So in this paper, they took this PCA1 component and used the rest of the components, added them up into a single signal, and then used that data. Yes, sir.
Can I just ask what transmitters and receivers are you using? Are these laptops, phones, or routers?
The receivers are laptops, and many of the experiments. Transmitters are the regular routers, the commercially available routers.
One experiment, one paper I remember they use even cell phone too, but I think majority of the cases they're using just the cell phone because laptops. Because laptops come with the NIC cards now, I think and NIC cards can easily capture the CSI signal. And at this point of time, I don't think there are any mobile cards available for a cell phone which actually captures the CSI data. I'm not aware of that. Yes, sir.
I have a kind of related question. Is it possible to use a mesh network, like multiple receivers and transmitters, for more accuracy?
So many of the research people are doing, even I think research what I'm doing too, is single receiver and single transmitter. With multiple receivers, if you have different types of signals coming in for the same activity, even though you get a lot more data, which is actually good for deep learning model, and hence, because you're not doing any feature engineering or feature extraction, I think it may make sense. But till now, as I mentioned to you earlier, there are not enough research being used, research using deep learning models. So the largest data set was 960 packets of data being sent to collect one activity information. That was using, I think, KNN, human classification with KNN. I think maybe this is the paper. If you have a multiple set of receivers receiving the same packets on different location, even if not right next to each other, different location, you may get more data, but I have not seen any published information. We are working on a similar case of a single receiver and multiple receivers, but we are inconclusive yet. We have not finished yet our research.
960 packets per second, right?
It's 5 gigahertz. So you actually have the frequency of your transmitter is 5 gigahertz. You actually have so many, we get, I think 100 packets per second. But 960 packets for that entire activity, when you actually, let's say you're walking, you walk for that long a duration so that you get 960 packets of information for the walking. So 960 packets, but you actually have 9 pairs of transmitter receiver information coming in, so you actually have times 30 subcarrier information for that. But 960 packets is what for one particular. So the one single packet you get 30 times, that is subcarriers, but you actually do it 960 times so that you get so much information. But that's the largest data I have seen people using. Not the typical deep learning models where people are using maybe hundreds of thousands or even millions of data, so that I have not seen. Maybe it goes back to his question too. If you have multiple receivers and transmitters, yes, you'll end up getting more data. Or also, many of these research, when they're doing the walking or the sitting, etc., they do, let's say, walking for 1 hour or maybe 5 hours or 10 hours maximum. There's no walking information of, let's say, 100 hours, because if it's a small lab setting, there won't be much of a variation in the signal if it's from 5 hours to 50 hours. Unless the lab setting or the room setting is wider, and if you have multiple types of people walking in, and hence, or multiple activities being tracked. The largest number of activities being tracked in the paper was only 4 activities: sitting, falling, I think a couple of other things. There was a paper published, and also there's a YouTube video available for detecting the keyboard, which key in a keyboard you're striking, and the model actually figures out. They actually had a very good accuracy, but the problem is some keys, they were showing better accuracy, because if the key is somewhere to the extreme far away or extreme left, if your hand and your fingers have to move, the model was a lot more accurate to figure out which key you are striking. But if your hands are right in the middle of the keyboard and then you're striking at the key right beneath your finger, then the model accuracy is very low there. But it's actually a good paper if you guys want to read about keyboard detection.
So are these the papers that you all talk about?
Yes, these are all some of the papers. Yes, these are all papers. I can't talk about my research, but I'll be actually talking about some of the information, what we are doing too. That's the answer. Yeah, that's the link for the paper. Yes, yeah. All my slides actually have links to the papers I'm getting the information from.
So is it true that you basically have to trade the model for every setup, for every environment?
Yes and no. Right now the research is for one transmitter, one receiver setting with a small room. You can have multiple types of people walking, but if your classification or detection is only for those 3 or 4 human activities, you can train so many number of people for so many number of hours. Let's say if it's sitting, you can actually have, let's say, 1,000 times or maybe 5,000 times sitting. And all of this research is being shown only to prove the effectiveness of the Wi-Fi signals being used and AI models, connect the Wi-Fi signals and the AI models to actually make predictions. Using it for a non-lab settings, I think I have not seen, I have not heard. I know the reason why it's not happening, because I think I'll talk in my last slide about some of the problems Wi-Fi signals has compared to, let's say, your audio signals or your video signals. This is slightly different, and that's why I think maybe the research is not going on. Also, I'll talk about a couple of other innovations that's happening in the deep learning world, image processing world. I don't know if you've heard of something called capsule networks. I think that also is going to come and change the way signal processing will happen going forward, but that's capsule networks were invented in October 2017, 4-5 months ago. Okay, this and there's one more paper I think were published in 2017. One of the first 2 papers where the real deep learning was used. I want to show you, I was mentioning earlier about the why CSI signal is better than RSS. If this is the standard deviation, if you look into 10%, if you only look at 10% variation, 60% of the signals in RSS will have only less than 10% of variation of standard deviations, but almost 90% of your CSI signals have less than 10% of your standard deviation variation. What does it mean? It means lot more amount of CSI signal data is stable enough compared to RSS data. That's the reason why people don't use RSS signals. But in this case, very interestingly, even for me, I felt very, it was kind of not sure why. Restricted Boltzmann machines, RBMs, were used as a machine learning model in this case. I have not heard of enough instances RBMs used as a deep learning model in numeric data or text processing data. So I was very surprised. I even sent an email to these guys and go, what was the reason why you picked that model and not some other model? I didn't get a response yet, but the entire process of data collection, denoising is very similar, and they've used RBMs as part of machine learning model. They got a very high accuracy response in this case. I think 95. All papers published are above 90, 94, 95% accuracy rate. So this is the most recent, or one more research paper which is most recent. This I want to spend a little more time to explain. This is the first paper, maybe you'll find more papers coming in. Instead of using just the phase of or the amplitude of the signal, these authors tried to use change in phase. It's called the angle of arrival. If you take the same packet received by 2 antennas right next to each other, if whatever phase angle the first antenna receives and the second antenna receives, compute a phase difference, the angle of arrival. That angle of arrival information is lot more stable and lot more consistent for activities they were trying to measure, even compared to the regular phase and amplitude of CSI information. So angle of arrival information was captured. That's number one. Number two, imagine a vector where for every packet you have 30 the 30 subcarriers, and if you have 3 receiver antennas, and if you want to compute a phase change or angle of arrival, it will be between 2 antennas. If let's say antenna 1, 2 and 3, thus the angle of arrival for 1 and 2, if you capture the phase and do, you can deduce the angle of arrival between these two antennas, and similarly between antenna 2 and 3. So for every packet, you have 60 angle of arrival data points for the same packet. And if they have 960 packets, and if you have, if you break those into groups of 60, you have a matrix of 60 by 60, and you have 16 such matrices. You want me to repeat that? Anyway, so you have, for every packet, if there are 3 antennas receiving, coming in, you have antenna 1, 2, and 3. The angle of arrival between antenna 1 and 2, you get 30 numbers, 30 data points, and between antenna 2 and 3, you get another 30. So you have 60 angle of arrival information per packet. And if you make that into one single column in a vector, and if you have 960 such packets, and you take a packet of 60 packets information. So for each packet, there are 60 data points, and you have 60 such packets. So you have a matrix of 60 by 60, and you have 16 such images, which is 60 times 16 is 960. So you have a matrix of numbers. This is the beauty of this paper here. They are converting the signal into an image, just a picture. And the picture in this case is a picture size of 60 by 60, and you're getting 16 images for the same activity. That is because it's the same packet you're getting. No, sorry, same activity. So if you have an image of 60 by 60 and you have 16 such images, the rest of the process becomes similar to any convolutional neural network model for image processing. So you have an image which is 60 by 60 and depth 16. You run a filter of 5 by 5 and you run 32 filters on it. When you run on this, you will get an image of depth 32 and the size 56 and 56. And then you do a subsampling layer. So you have a convolutional layer, C layer, and an S layer. And for every convolution, you have a subsampling layer. And if you take this pair as one unit, you have 4 such units. So you have a convolutional layer, then subsampling layer, another convolution layer, another subsampling layer, and it goes on till 4 times. You have 4 such processing, and then you connect it to a fully connected layer to make a prediction on what this input image is about. So if you have read CNNs for, let's say, classification lots of the cat or a dog or a car or an airplane, this entire signal processing problem is converted into a CNN model. I am expecting a lot more papers, and there's a lot of potential for this type of approach. And also, if you look into the accuracy of the model, you have the cumulative distribution function of sci-fi, and compared to other models which were published earlier, DeepFi was the paper just now I mentioned, the accuracy rates is almost 80% for an error rate of around 2.5 meters. In other words, the model can predict with 80% accuracy with an error of 2.5 meters. And if you don't mind an error of, let's say, 4.5 meters, it can predict 100% of the time where the person is located. There's a lot more research yet to happen to make the models correctly. At this point of time, whether it's amplitude only or phase difference or a combined CSI, the research is not agreeing on a single factor, and a lot of people are trying to predict what would be a good indicator. Angle of arrival, like as I said, phase differences was one indicator used by one paper. But because the signal is still getting affected by so many other environmental situations like temperature and objects and obstruction, either the models have to be fine-tuned or the data that's coming in has to be fine-tuned. The deep learning models at this time, I've seen people have used, people have not used LSTM yet, but CNN I think being used. Capsule networks, which was announced in October 2017, has a lot more potential. One benefit of capsule network is traditional image processing models always needed maybe hundreds of thousands of data points or even millions of data points. Capsule networks need, in best case scenarios, a few dozen, or in a worst case scenario, maybe a few hundreds. So if you have even less amount of data and using the effectiveness of the capsule network, I think you may find better models coming up, but that's what I'm waiting for. Generated adversarial networks is another approach being used, where you can use, you can have one model generate the data what you're looking for and feed that data into another similar model, which actually starts getting better and better. So if you are creating a human activity detection model for signal processing, then you can have one model which actually creates more CSI data, more and more accurate data, and start feeding that CSI data to the model. So you don't need as much of data going forward. Reinforced learning is another hugely popular topic in deep learning model. You might have heard of the game of Go, which was learned, I think, in a few hours, and it beat the world record holder. I think similar RL models can be used for signal processing too. There's two fundamental problems I've heard is, even though people are trying to figure out the connection between the CSI data and the human activity, there is no absolute indication that CSI data indeed is a reflection of the human activity. In other words, if you take the lab environment out and put new people, or you expand the lab to a bigger room or a different room, there is no indication that the model is going to work. So till now, all the papers published are only shown in the lab environments. And sometimes, right now the models are only, sitting and walking and standing. What if you have a room full of people like you, and each one is doing different thing? If you want to have a model to figure out what each person is doing, a person is breathing or not, or someone is checking the email or cell phone, or someone is talking, someone is sleeping, I think it's a lot more complicated. I think signal processing is in a very early, really early stage of development. I think maybe it will take more than 2 years to come before people, you can start seeing models figuring out human activities in a complex environment using signals. Yes, sir.
What are some other applications other than human behavior? Have you maybe tried to integrate in mobile phones, Wi-Fi, something else?
Good question. I think the focus, the answer is I don't know. I don't know what other activities you can use, but there's a lot of interest in figuring out what human beings are doing and using it for the good of the human being without getting into the problems the image processing is getting into of privacy and maybe lighting and the line of sight issues. But for example, healthcare scenarios, if you want to have patients being tracked but you don't have so many trained doctors available. Let's say you're in a child care situation where the kid is playing on his own, but you want to have, or a security concern. Let's say in an airport, you want to track people, certain untoward incidents to be tracked. The AI models, the situations where AI models being used using audio, text, and image processing, all are being focused on human beings because you want to alleviate the problems of human beings, I guess, and that's what I think the signal processing is also going towards. But other than that, I cannot think of any other situation where you can use this signal processing. Right now, I think all AI is being used to see how we can make human life better. That's what I guess, yeah. I don't know the answer, yeah. That's all I had for today. If you have any questions, I'll be happy to take. Thank you.
What your research? What's it about?
Sorry?
You say you will let me know about your research.
So we are focusing on collecting this data and to use LSTMs. If you have seen, I did not find a single paper using LSTM because in signal processing, the activity always is a temporal activity. It actually takes some time always, and in deep learning models, I think LSTM would be even CNN is not a temporal thing. You can actually have an image at any instance given, feed into a CNN and make sense out of it. But LSTM is one of the few, of course, GRU is another model, one of the few which actually can process temporal information. And if I were to give an example of a temporal information, if a text information could be, the cat sat on the mat sat on the cat mat sat on the. Even though all three examples are the same words, the first sentence has certain meaning, the second sentence has another meaning, and that sequence and the information that captured in the sequence will be appropriately captured in LSTM, and I think there is a lot of a temporal aspect in signal processing which is not being captured, and that's what we're focusing on.
Maybe this is a little naive, but I don't think that there's necessarily a correlation between CSI and human behavior, because that's a measure of trying to get information across from one antenna to another, and you're just kind of hijacking and taking advantage of it.
Yeah.
In your optimal world, if you could place some sort of tweak on the way that the information is actually being sent, but you still preserve optimality within some reasonable window of data transfer to detect human behavior, what would you do?
I don't know. What would I do to get the
To change
optimal-
change the output signal to still be able to transmit data efficiently, but
let me give a long answer for that. There is a famous quotation in statistics. It's called causation. Correlation is not causation. Just because an activity is correlated to another activity is not causing it. But correlation would be a good area of study, because if the correlation is very, very consistent, then you will be absolutely sure, okay, this is what is causing it. But till now, based on the research, they are able to find some correlation, but there's not enough research to prove that this correlation works absolutely in every situation. For example, if the signal moves violently towards the last few milliseconds up and down, and the amplitude and the phase is X and Y, let's say, for falling, if that is what is exactly happening for when the person is falling down, that's what is impacting the CSI, then the model, we can be absolutely sure that there's a model now, it works for you. And even though I did not do research on your falling or you're falling or you're falling, but the model will figure out exactly when the patient A and B have fallen, even though he never saw the patient A and B. That correlation, because in signal processing engineering, people I think have not figured out the correlation. Now, if your question is, what would I do to find the optimum correlation?
no, my question was, what would you do to change the Wi-Fi signal behavior itself to make it more I don't know, to pick up on signal better for human activity?
Good question. I don't know the answer. I don't think I know what I will be doing. But if I look into my AI journey, where we are trying to solve problem used on data, numeric or text or image, on all my research and I think the whole of AI world's research going on is, okay, I have what I have the data, whether it's a text or image. Can I find correlations, consistent correlations in such a way that I can define a model that if I see this is what it means. Even though that's not what exactly is happening in the background, that's what, so for a text, let's say if you have a language or an image, because the signal that's coming in, the data that's coming in is a lot more reliable for a text, because you actually can see the text. If it's image, you can see the image. We don't know how much of noise coming in. People I think have figured out some noise, but we don't know what else is there in the signal, and they're using that. So you have the authentic, real information plus some noise being used to develop a model, and hence that's why sometimes the accuracy rates are varying. But what would I do to change the data? I don't know. I don't think anyone has actually answered. Good question, actually. Maybe I should put it in there.
You could put in multiple, Wi-Fi signals, one of a different frequency, and then compare them. That would tell you, how they're differentiated. Mm-hmm. So I don't know if you've heard about radars, which there are sensors which do that. So you can use a continuous wave radar, and you can use a pulse radar, should tell you the difference in the signal.
Okay, thank you.
Yes, sir.
Is there anything unique about the human? Is there anything unique about the human body that makes this detection possible? Like, can you distinguish between a large object falling off of a shelf?
Good question. That is one of the unanswered questions in the signal processing for AI world. If a person of, let's say, a slim person versus a large person is walking, signals are not similar. In some situations for walking, maybe I think they're not similar. Sometimes they are dissimilar. In other words, the signal variation is not consistent to show, okay, for a tall person, for a short person, it's different. For example, if a short person is walking, rather sitting, let me change it. Let's say a short person is walking versus a tall person sitting, model will think both. The signals will look similar. Some of the examples I've shown. So what is making in the human being is making it distinct, that people have not figured out. That's one of the problems, because what is that in the human being that's making the signal distinct? Then you'll be able to figure out, okay, for walking, this is what is impacting the signal, and for sitting, this is what is impacting. Right now, we're just, in all the research engineers, AI engineers like me, we're just collecting the data and we label it, okay, this is the signal I got when the person stood, and this is the signal I got when the person fell down, and say, can I see if this falling signal is consistent all the time, and how many times it's consistent, and can I develop a model out of it? That's what has been the approach till now.
But the frequencies are not tied to human body, it's just tied to the receiver location. Because the frequencies are low band frequencies, you're not able to. I mean, the testing that you've done is, or results you're showing are on, devices, not on human bodies, right?
The testing is of the signal received at the receiver after reflected by a human body. So let's say if you're typing, if you're washing dishes, if you're talking, if you fall down, or even if you're breathing, signals are a reflection from the human body, and then they're trying to look at the CSI value of those reflected signals.
How they're doing that? Because you're using a laptop or something to recover. So how do you know it's a reflection or a multipath or it's a body?
They are
or
averaging. Yes, you're right. That's the problem. They are averaging the CSI values or the signals they're getting from multiple paths. Multipath impact is one of the biggest problems for the signals. Yeah, that's fading, multipath. These are some of the issues which, compared to, as I mentioned to you earlier, image processing, where you actually get an image, and that's exactly what you are looking, because you can actually compare the image with the real situation.
So now, if you have Wi-Fi cameras that have high quality video, this problem does not exist. You can just take the video and you know what's going on.
Well, but then it goes back to my original problem. I said video is a privacy issue. Yeah.
But in a hospital where it's a patient care, you already have the video feed.
Then we're getting into a non-AI discussion where it's more of an ethical, moral, all of this. But even in a healthcare situation, let's say if it's dark, like the patient is sleeping, it's night, you can't have the model. Or if the patient, let's say if the line of sight is another issue too, because for the camera, if you can't see, the camera cannot see, it cannot predict. Whereas Wi-Fi signals can.
But I think you can combine the camera feed to get you better estimation.
You're right, that's a good point. In the lab situations, for labeling purposes, people are actually taking a video. You either have a human being detect, okay, what time the person is sitting, or you actually have a video camera watching when the person is sat down, figure out the timestamp, and then use the timestamp to get the signal. For that purposes, lab experiment purposes, you can do it. But in a real situation, there are distinct advantages using Wi-Fi signals compared to video. Yes, there's a lot more research that has happened in video, and hence maybe I think the accuracy and reliability of the video is higher. But I guess there's a lot more potential for the Wi-Fi signals to go going forward. And we are in such an early stage. Some of the problems, why had they have not done it, we don't know. But having said that, all the published papers, you never know what did not work for them. They publish paper only what worked for them. And hence, we don't know when we want to do experiments. Let's say if I want to do an experiment, if you are a researcher, if you have published a paper, I would not know what did not work for you so that I don't repeat the same problems. But that happens. Of course, some collaboration can happen and people will figure out. But
in the paper only talks about what worked.
So there's you said there was like a resolution issue, right? So like when you do image processing, like if you have high quality video, like you said, like you can see like everything to great detail, right? But like is the resultant image that you get from the Wi-Fi, is that high resolution too, or is it not high resolution? Comparable to video?
At this point of time, the resolution itself is not a major factor in image processing.
Okay.
And I'll tell you an example. In 2016, in image processing world, the average accuracy of an image processing model is better than human being. Human being makes an error of approximately 5.6 per 100. In other words, if you give 100 pictures of, let's say, dogs and different shapes and colors and stuff, 5% of the time you may not be able to predict. But the model will make only an error of 3.6% of the time. So what does that mean? That what can it be more than human being? If I can predict, how can the model predict better? The answer is, human beings cannot predict accurately if the image is blurred. Whereas the model can actually see, even if your naked eye cannot see, but the model can see what is in the picture and reconstruct. So next time when you send your pictures, if you don't want other people to see, and you think, oh, I have blurred it and I'm sending it, think twice, because machine can see it. And if it falls in the wrong hands, then the model can immediately figure out what pictures they are. So I have seen image processing experiments with 224 by 224 pixel size and 1000 by 1000 pixels. So that is 10 megapixels versus less than a megapixel size too. In both the situations, model is extremely intelligent to figure out what's happening. So of course, you cannot make it small, like 10 pixels by 10 pixels. I think it's maybe, I've not seen experiments of that size, but smallest is 224 by 224 pixel size. So model can emit. So the pixel size or the size of the image is not a differentiating factor anymore for the model to be accurate, as long as you're getting the data correctly. In signal processing, even though you convert the signal number into images, those numbers are not consistent enough. Like, for example, if you give an image processing a picture of a dog, and if you have 100 different dogs, all are definitely dogs, and you tell the model this is a dog, and then model can figure out. But when you give signals of a person sitting, let's say 100 examples of a person sitting, but the signal you're capturing may not be an exact reflection of sitting, because you're also giving noise to it. And that's where the problem is. And we don't know what the noise, how much more noise is in that. And we don't know if the signal coming, let's say human reflection plus the wall, reflected from the wall, reflected from the human being, and you're averaging out all this information, so you're actually bringing in yourself some noise. And that's where is the whole problem.
Do we have any more questions?
Thank you, guys. Thank you very much. I appreciate it.
Thank you.